experiment focuses on flow over a cylinder using the Cal Poly low-speed wind tunnel, with flow directed normal to the cylinder axis. But first, we'll cover some background. In the real case, since the cylinder is considered a bluff body, the flow cannot stay attached to the surface and will separate from the cylinder at a certain point, depending on the flow properties. As such, we'll get a net force form pressure drag in the streamwise direction. The plot shown displays the effect that Reynolds number has on drag coefficient, which for a cylinder is rho VL over mu, where L is the diameter of the cylinder. Please note that log scales are used on both axes. As Reynolds number increases, drag coefficient decreases until about 1,000, and then stays constant around a value of 1 until around 100,000. When examining Reynolds numbers lower than 200,000, the flow is considered laminar and viscosity is the dominant term in drag. In this regime, flow separation occurs at about 80 degrees from the front of the cylinder, the stagnation point. And in this lab, we'll be looking at two Reynolds numbers and their effects on drag. We will also be adding a trip strip to our cylinder in order to cause turbulence before separation and observe the subsequent effects. Another important phenomenon we will examine involves the formation of vortex streets. Separation occurs simultaneously on the bottom and top of our cylinder. While perfectly balanced, vortex shedding does not occur, but due to the highly unstable nature of the separated boundary layer, any pressure difference between the top and bottom locations results in the accumulation of a discrete vortex. This then travels from one separation location to the other, oscillating back and forth with a variation in pressure. Vortex shedding is a function of Reynolds number, such that at low values, the vortices experience minimal oscillation. As Reynolds numbers increase, the pressure differences become more pronounced, resulting in higher frequency oscillations. Eventually, however, the turbulence of the flow overcomes the orderly nature of the vortices, thereby reducing their prevalence in size.
Procedure, we decided to run at 2 different RPM settings in order to compare results. In these 2 settings, we conducted tests both with and without a trip strip fastened to the cylinder. In this experiment, the trip strip was simply a piece of wire fastened lengthwise across the cylinder about 85 degrees, as shown here, above and below the stagnation point. In an ideal experiment, this trip strip should be placed closer to 75 degrees, about this location, from the horizontal. For each of the 4 cases mentioned, we ran the test 3 times in order to obtain repeatability with the data. With our velocities and with the cylinder diameter about 4.5 inches or 0.1143 meters, as well as with our calculated ambient conditions, or density from pressure and temperature, as well as an estimated dynamic viscosity, we were able to obtain Reynolds numbers in the range of 53,000 for the slower case and 180,000 for the faster case. These are both values which fall in the range of laminar to low transitional for a flow over a cylinder, assuming the flow does not possess any unwanted disturbances. Because our main concern here, data-wise, was looking for a coefficient of pressure and drag calculations, it was important to understand our pressure measurements. We used static pressure ports, which means our pressures obtained were referenced to the free stream pressure. Thus, our data is essentially P at the port minus P infinity, as shown in the equation above here for coefficient of pressure. This makes calculations for pressure coefficient very simple, as it requires only dividing by 1/2 rho v squared, or dynamic pressure. It is also important to understand propagation of error in our calculations. With this scenario, we will use standard deviation as a measure of variation and uncertainty. Because we are assuming density to be nearly constant, we will not propagate uncertainty in this variable. However, we do have existing standard deviations for our static pressure readings, as well as for our free stream velocities, which are squared in the denominator of this equation. As such, using error propagation formulas, we came up with the following formula, as displayed here, where we will use this formula to display error bars that represent one calculated standard deviation on our coefficient of pressure plots. A second goal in this lab is to determine the coefficient of pressure drag and the pressure drag forces for the flow on the cylinder. It is important to note, as before, that for our Reynolds numbers, friction drag is not negligible. However, since we are looking at pressure in this lab, we will only be looking at the component of drag derived from pressure. In order to accomplish this, using our pressure data, we used a low-level panel code method. But since our CP values are already calculated with uncertainty and variation propagated throughout, we will take a more original method. Essentially, we have 24 pressure measurements, where pressure is force over area. So if we multiply these pressures by an area, we can determine a force. The only extra consideration here is that we need to take only the component of force in the streamwise direction for drag. As such, we took pressure at each port and multiplied by the cosine of the respective angle. Next, each streamwise pressure was multiplied by 1/24 of the total lateral cylinder surface area, 2 pi RL. And then these drag portions were all added up for a total drag. Finally, to get drag coefficient, we divided drag by the appropriate dynamic pressure times the frontal area of a cylinder, since it is a bluff body, which is diameter times length. The final goal in this lab was to pull some qualitative and quantitative data out of flow visualization with the smoke machine and a laser. At our Reynolds numbers, as shown in this figure, we expect to be in the 300 to 300,000 range, which defines fully turbulent vortex shedding. Through video examination, we will look at separation points on the cylinder, as well as what this means for the flow of properties.
As previously mentioned, the first thing we will look at are CP plots versus data. The image seen now displays our coefficient of pressure for the runs without a trip strip. Note the two Reynolds number run at for 200 RPM, 54,000, and for 600 RPM, 180,000. As discussed earlier, both of these are in the theoretical laminar range, though the upper value is very close to the low transitional regime. A couple things to note to this plot. Separation occurs on the top, left side of the plot, at about 72 degrees, where there is a clear bump in the trend for both RPM settings. But on the bottom, the right side of the plot, it occurs closer to 300 degrees, or only 60 degrees from stagnation. Both of these values are much smoother than expected for laminar flow over a smooth cylinder, but we must remember that we are dealing with some surface roughness here, which may have forced earlier separation. Additionally, the asymmetry of the separation displays a symmetry in the flow over the cylinder, which displays the wind tunnel's own asymmetry and/or the fact that the cylinder may have been placed off-center vertically in the tunnel, positioning it such that more air flows over one side than the other, and at a different velocity. The three plots of each simulation are very close together, which makes us confident in our repeatability. But notice that the propagated standard deviations of the lower RPM setting are on average 2.3 times those of the higher speed setting. This is likely due to the large effect of fluctuations in the wind tunnel have for lower speed, lower strength flow. Finally, notice that the coefficient of pressure on the back of the cylinder for the lower speed cases are more negative, meaning lower pressures. This causes us to believe that 600 RPM cases actually reached a low transitional regime where some momentum in the direction normal to the cylinder would allow some flow to stay attached to the cylinder longer, plus increasing pressure on the backside and creating less negative CPs. Now we move on to our cases with a trip strip.
Again, the Reynolds numbers are given in the legend and are both still in the laminar to low transitional regime. A couple of things to note. One, again, note the asymmetry as the flow separates off the top at around 85 degrees and on the bottom at about 60 degrees. However, note on the left or top side that there's a flat part before the bump for separation. We think this additional pressure is from a bit of air which recirculates backwards before the separation point due to its rebound off the wire. Number two, note the variation in the high RPM case, which is unprecedented in our data so far. We think this weirdness may come from the trip strip being buffeted and moved by a bit of faster, stronger flow, creating a lot of variation and fluctuation in the pressure readings between runs. Note that the three lower RPM cases are still very consistent. However, like last time, the mean standard deviation, shown in the error bars, for the lower RPM case is 1.25 times the mean standard deviation for the high RPM case. So despite fluctuations caused by the trip strip wire, tunnel fluctuations at low RPMs is still a more prevalent source of imprecision. Number three, finally, note again that the higher RPM cases, which could be the low transitional regime, have noticeably higher pressures on the backside of the cylinder, potentially from some small bit of flow which does not separate as much. It is also important to compare trip strip to no trip strip cases, so our next plot will feature one run of each 200 RPM with trip, 200 RPM without trip, 600 RPM with trip, and 600 RPM without trip. Things to note. One, note the smaller standard deviations without trip strips, which confirms our idea that the trip wire caused more fluctuations by creating a barrier in the flow and possibly a small amount of recirculation. Number two, note that overall trip strip cases have less pressure on the rear of the cylinder than the no trip strip cases for their respective RPMs. This is contrary to what we believe would have happened if the trip strips had been placed further forward before the separation point. Instead, it seems that rather than creating a small amount of beneficial turbulence in the flow to allow for a later separation point, the trip strip created more turbulence in an already separated flow, resulting in lower pressures behind the cylinder than in the front. If this holds true, we should see higher drag with our trip strip situations than without. Upon calculating drag forces and coefficients in the manner described previously, we got the results in the table shown below. As expected, we obtained higher drag forces and coefficients in the trip strip cases versus the no trip strip cases. The placement of the trip strip was certainly after separation, which is what causes our results to be opposite of expected. However, one interesting point is that all our CDs are in the 1 to 1.7 range, which is exactly the range that the Reynolds number versus CD plot for a smooth sphere that we showed earlier predicted. Finally, note that, as expected, we get lower CD values for higher RPMs or higher speeds. This again is because the higher RPM setting lies in the low transitional regime, which could allow for some of the flow to stay attached longer and thus larger pressures on the back of the cylinder.
As you can see in this clip, a Kármán vortex street exists behind the cylinder. The free stream velocity is 15 meters per second, and the Reynolds number at the cylinder is 100,000. The wake appears to be fully turbulent, which is expected at this Reynolds number. The frequency of the vortex shedding appears to be 3 Hz and is proportional to the free stream velocity. Separation occurs before the flow reaches the backside of the cylinder at approximately 80 degrees from the horizontal. The team found that, overall, it was difficult to obtain quantitative data from the flow visualization. In conclusion, we were certainly able to observe, through quantitative analysis, a difference in the coefficient of pressure distribution and thus drag between the tripped and untripped cases. Initially, we expected the tripped boundary layer to cause less pressure drag than the untripped boundary layer. However, the experimental results were the opposite of what was anticipated, in that the tripped boundary layer actually caused more drag than the untripped boundary layer. This was most likely due to incorrectly placing the trip strip behind the separation point on the cylinder. The standard deviations for the tripped case were, on average, greater than the standard deviations of the untripped case. This is likely due to the unsteady conditions that are characteristic of turbulent boundary layers, which was only increased by the trip strip wire potentially not being secured perfectly, and thus vibrating. Additionally, we were clearly able to observe the Kármán vortex street through flow visualization. Although not much quantitative data came from the video, this vortex street did closely match the expected wake profile for this Reynolds number.